All right, so last video for tonight, and we're going to be talking about how we can look at an acid or a base and know something about how weak or strong it is just by understanding its structure. So up till now, you've just been memorizing this is a strong acid, this is a weak acid. Now we're going to have a little bit better understanding of that. So let's kind of jump right into our PowerPoint here. And what we're talking about is how what's in the molecule affects its acid-base properties. And this one really is pretty simple. The most significant factor that influences the strength of acids and bases is electronegativity. So hopefully we all remember that the most electronegative element on the periodic table is fluorine, and that electronegativity increases across a period as we go from left to right and increases from the bottom of the table to the top. So particularly when we talk about acid strength, electronegativity is very significant. If we have a binary acid, meaning that it only contains hydrogen and one other element, there are two factors that we need to consider. One is the polarity of the hydrogen to something bond, and the other is the strength of the hydrogen to something bond. So the more polar the bond, the easier it is to break. The easier it is for water to break it and release that hydrogen. The strength of the bond, the stronger the bond, the harder it is to break. So the weaker the bond, the more acidic the compound is going to be. So you'll notice that as we go across the table, polarity is the key. The radii are really similar, so it's the polarity of the bond that matters. As we go across the table, that polarity increases and therefore the acid strength increases. But as we go down the table, so if we were to think about the halo acids, hydrogen fluoride, hydrogen chloride, hydrogen bromide, it really is about the strength of the bond. And as the so we have both of those factors being considered. So hydrogen fluoride is a great example. It's a very, very polar bond, but it's a really short bond, which means that it is a really strong bond. So strength trumps the polarity there, and hydrogen fluoride is a very weak acid. What about if it's not a binary acid, if it's one of our oxy acids? The strength of oxy acids is also dependent on that electronegativity, but in a little bit of a different way. So if we think about it, an oxy acid and a base has the same fundamental structure. If we look at sodium hydroxide, we have a sodium attached to an oxygen attached to a hydrogen. If we look at hypochlorous acid, we have hydrogen attached to oxygen attached to chlorine. So why is one of these an acid and the other is a base? Well, in water, our more ionic bond, so our more polar bond, is the one that's going to dissociate, and that's what determines whether we have an acid or a base. So because we have this big difference in electronegativity between sodium and oxygen, in sodium hydroxide, the bond that's going to break is the bond between the sodium and the oxygen. But if we look at hypochlorous acid and we look at the differences in electronegativity, the hydrogen to oxygen bond is more polar than the oxygen to chlorine bond. And so the bond that's going to break is the hydrogen to oxygen bond. So that difference in electronegativity determines which bond is going to be broken in water. So what about alcohols? So we have carbon attached to oxygen attached to hydrogen. Is this going to be an acid or a base? We have a similar structure. Truth is, this difference between 2.5 and 3.5 and the difference between 3.5 and 2.1 means that they're not very effective at either. Most of the time, alcohols don't behave as acids or bases. They will occasionally act as acids. They are very, very weak acids. With Kas, in the range of 10 to the negative 15th to 10 to the negative 20th. So really, really, really tiny Kas. So they are effectively not really acidic or basic. Okay, so we now know that the more polar bond is going to break. We also know that electronegativity matters. So let's talk about when we have these acids, particularly oxyacids, that have increasing numbers of oxygen atoms. How does that come into play? Well, when we have only one oxygen atom and one chlorine atom, this chlorine is extremely electronegative. It's really pulling the electrons towards itself. So it's making this oxygen to hydrogen bond ever more polar. But once we add in another oxygen atom, now the chlorine is able to pull electrons from both oxygens. It's not pulling as hard on the electrons in, sorry, let me try that again. It's pulling even harder on the electrons in the oxygen, which is making this oxygen to hydrogen bond even more polar. And we move to chloric acid, which we know is one of our strong acids. Again, more oxygens, more electronegative, pulling even harder. So this hydrogen to oxygen bond is even more polar, making it even more acidic. And finally, we reach perchloric acid, which has the most oxygens and therefore has the weakest oxygen to hydrogen bond, or most polar oxygen to hydrogen bond, and therefore is the strongest of these four acids. So one way to think about acid-base properties is to think about how polar or how strong or weak that oxygen to hydrogen bond is. Another way to think about the strength of acids is to think about the stability of the conjugate base. So the more stable the conjugate base is, the smaller the Kb is going to be, and therefore the larger the Ka is going to be. So if we have higher electronegativity atoms attached to whatever, whether it's an oxygen or a carbon, we're going to have a weaker conjugate base because those electrons are less accessible for the protons in solution to bind onto. So that means it's not a very good base, which means that its conjugate acid is stronger. Also, the more electronegative so kind of looking at it from the other side, the more electronegative the element is attached to the X, the more acidic the oxyacid is, because the electron is being pulled away from that something to hydrogen bond, which makes the something to hydrogen bond more polar and therefore more acidic. And then our last consideration is when we have polyprotic acids. So we have polyprotic acids, successive protonations, so the K2 and the Ka3, those are always going to be weaker because we're removing the hydrogen ion from a negatively charged ion. So I'm trying to pull something positive away from something negative. And the more negative that ion becomes, the more strongly attracted that hydrogen is going to be, and the harder that is going to be to break. So I hope that helps with structure. We'll be discussing this and doing some practice problems with it tomorrow. As always, if you have any questions, let me know.